Episode 2, Gravitational Waves. You're listening to SPEXcast. Welcome to SPEXcast, a podcast for discussing the science and technology of space exploration. I'm Phil, and joining me today we have TJ.
Hello.
Waving doesn't work on audio, TJ.
I will keep waving for as long as they can't see me.
And we also have James joining us.
Hello.
And today we're going to explore the topic of gravitational waves.
That's right.
So, gravitational waves are a relatively new discovery. We've theorized that they exist for a long time.
Right.
And just now, recently, we have proof.
Exactly. February 11th.
All right. So,
Yeah.
so James, you're kind of the expert in the room. Can you
A little bit.
talk about this topic? Yeah.
Well, basically, gravitational waves are essentially like ripples in space and time. And you have to suspend your belief about space just being a linear place. You can travel from one place to the other without going in different directions. It's curved. There's a curvature to space-time. And it's a very complicated matter. I don't know a ton about it myself, but I do know a little bit from my reading. And what I can say is that it's a very, very complicated but cool topic. Mm-hmm. And RIT has a lot of gravitational wave research in our CCRG, which is the Center for Computational Relativity and Gravitation.
So do they do experiments there, or is it mostly research and like playing with the math and looking at other people's data?
What they do there is actually they have a huge supercomputer. I don't know if many people don't go there. It's a very kind of isolated part, but if you go there, there's a huge glass door, and beyond that glass door is like several walls of computers. And what they do there is they analyze data that we just got from LIGO and the other Gravitational Wave Observatory.
So LIGO, that's in DC. They have this
Right.
big laser contraption. That's what's been in the press releases, right?
Yes, it was.
Yeah.
And what they do is they create simulations on their computer of what gravitational waves could look like. And they did this before the actual discovery. They did it theoretically. And when they discovered the gravitational waves, they were actually able to prove that what they had simulated on the computers was real. And their simulations were very, very accurate.
Wow.
Yeah, it was very cool stuff.
As much of a feat of
Absolutely.
Simulation as it is.
Absolutely. Yeah.
Research. That's very interesting. So
It is.
just gravitational waves, the way I think about it, I know I have a little bit of an astronomy background, and I'm reading Stephen Hawking's A Brief History of Time. So I kind of know what's going on. Space and time are connected, and it's like this. It's not just three dimensions. You've also got time in there, and it can be warped and things, and it's affected by gravity. That's why when light passes through the universe, a big thing like a star can actually bend the light. The light follows space. So gravitational waves, if you think about like light passing and curving and following space, gravitational waves are ripples in that space. So you have two black holes, I believe, is what was observed. They're
Of course. Yep. A merger.
So they're
merging.
Yeah, they just like come together. Or you said they spin, right?
Yeah, so when black holes merge, they don't just collide with each other like instantly. It's not like two balls hitting each other at high velocity.
Right.
What happens is as they get closer to each other, they start to spin because a black hole's gravity is incredible.
Yeah.
I mean, beyond anything else. So what happens is the gravity actually twists the other black hole, and then vice versa. So what happens is as they get closer, they start spinning much, much faster. And the closer they get, the faster they spin until they get close enough to actually merge.
So why does that ripple? Wouldn't it just make a bigger hole?
It would once they merge, but before they merge, they are distorting space-time by waves, and that's what gravitational waves are from. Not only black hole mergers, but that's a huge contender, and one that we can sense from millions of light years away, billions of light years away, of course. So it just speaks to the immensity of these black holes and how much power they have in space and time.
So TJ, this is not your area of expertise by any means. You're a hardware technologist. What do you make of all this?
I think it's really cool. When I heard the announcement, I heard the announcement of the announcement, did some reading, actually read the announcement. RIT had a little press conference here for our contributions. I really like physics, and I'm totally intrigued, right, about the nature of gravitational waves. But the part that I can, really wrap my head around is the actual setup of the detector, which I thought was really interesting.
Yeah, do you know about the detector? I was about to ask.
Yeah, so I read about LIGO, and it's a really interesting setup. It's based on like some high school physics principles, really. So basically, you have a laser that shoots a beam down a long tube, right? And that laser is bounced off and then sent through a prism down another tube, and then bounced off again. So theoretically, and ideally, you have two beams of light recombining.
And they're out of phase with each other.
Yeah, at 90 degrees. And so if they're 90 degrees out of phase, both of those fields would cancel each other out, and you would detect no field.
Yeah, because when you superimpose two waves, you add them together, and if one's going up while the other's going down at exactly the same amplitude, it's just zero.
Right.
So if there's any disturbance, you see the laser, and that's a positive detection. But what about like an earthquake or something like a big truck driving down the road? Do they detect that too?
So with LIGO, when they first built the one, I think in Kansas, Kentucky, someplace
Hanover, I believe.
That's Virginia, right?
Virginia, I think so.
There's two,
Maryland,
aren't there?
maybe?
Yeah, there are two.
There's one near DC, and there's one, I think, someplace in the south. Anyways, they had a very big issue where they built this massive, because it's, several thousand feet long hallways, right, underground. And they had this issue with earthquakes and, big trucks driving around and other physical interactions. And so they had to build dampening systems into it to cancel those out, right? Because you're talking about even the best case, like minuscule measurements, absolutely minuscule. And so it's absolutely critical to have as big as a detector as possible to get that big, change and as sensitive detectors as possible. And that leads to, noise.
Yeah, so something I kind of want to ask you, James, is when you have a big laser that they're canceling each other out, if there's any disturbance, it moves. But how would a ripple in space-time, like a warping of space-time, cause a detection?
Well, the system that we've been talking about, the lasers, is actually called an interferometer, and it measures. It measures changes in distance, very, 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 very minute changes in distance, which the gravitational waves make. And when this happens, as you said, you can observe the laser, and that's when they know they've seen it. But as you guys have been talking about, noise from the Earth is very loud compared to what's happening billions of light years away.
Right.
So we've had to continuously increase the dampening system on the LIGO Center and the other. And it's taken many, many years. I believe somewhere around 40 to 50 years to get it to this sensitivity, to be able to pick up the gravitational waves. And of course, we've needed the gravitational waves just to be in our proximity. And it's a very cool instrument, and they've used it for several other discoveries too.
So on a much smaller scale, on a much more practical, applicable scale to us, is that the same laser interferometer setup is what makes the principle of laser ring gyroscopes. And when in our day-to-day business of designing satellites, gyroscopes and rotation detection are very important.
Rotation detection?
Yes. And so with the LIGO, they're looking for a gravitational wave passing through the detector, causing the aspect of the laser to change.
Right.
With a laser gyroscope, rotating the entire device through space is what causes the change. And so laser ring gyroscopes are super precise, and they're used for a lot of more expensive spacecraft that need that precision.
So the precision technology developed with the interferometer it can be applied to
the same physical principle that LIGO uses for gravitational waves, we use for our gyroscopes.
Cool.
Very cool.
So this discovery was just recently made or announced, right?
Right.
Two questions here. One is, has the data been measured a long time ago? We just now proved that it's from a gravitational wave? And second, has it taken so long since they were theorized because the technology wasn't developed and because the event hasn't happened? Like, is that what's contributing to it taking so long?
Well, actually, both are definitely contributing. The interferometer has been around for, I believe, over 100 years. I mean, Albert Einstein used it 1905, early 1900s, and it's been continuously being advanced in its technology, and that's been one major assistant for observing very small changes in space and time that we can't observe with our naked eye. And absolutely the technology is needed to advance a lot in the past 100 years, and it has. Absolutely, the past 40 years I believe we've been advancing very, very quickly. And to your first question, the data I believe was discovered in September, and they've been analyzing it to make sure it wasn't just some noise, maybe from a supernova, or maybe from just a truck on the other side of the Earth. You know, it's such an incredibly sensitive instrument that it could be picking up something else. And
now they've finally proven that, hey, this isn't a fluke, this isn't noise, this is the real deal.
Right.
And so now they're announcing it.
Now they announced it, right? Wow. And I believe they probably figured it out February 10th. Got very excited. Released it on the 11th, right? Yeah.
It's really interesting using this interferometer technology and the applications it's had over time.
Yeah.
Because the main principle is being able to measure very, very small changes
in distance.
And so something I was reading a while ago is that how did we prove the speed of light, right? We all know that's the universal constant that applies to everything.
Right.
However, going back to light as a wave, right? As humans, we deal with waves all the time. This podcast is all about, sound waves.
Right.
And that involves waves that can propagate through matter, through medium. And so when they were looking at the behavior of light, they're like, light behaves a lot like a wave. However, in outer space, there doesn't appear to be a medium for them to go through. And so they propose, well, there has to be a medium. Maybe it's something we can't find, right? And so there's this idea of this ether. And so that was the leading theory for how light waves propagated. So there's something called the Michelson-Morley experiment, which is basically what LIGO is on a much smaller scale. So if you are moving around the surface of the Earth, right? The Earth is turning, you're turning. If you shot a laser at something and came back, it would inherit the speed of the Earth and come back, right? If you shot a laser perpendicular to the turning of the Earth, it would move at the same speed it originated at and come back. So the theorem, the hypothesis, was that the laser going with the velocity of the Earth should arrive faster, and you get a reading on your interferometer. However, because of relativity, both beams of light come back at the same time and interfere, so there was no measurement. So this exact same technology is what proved
the speed of light.
The speed of light and general relativity, I believe.
No matter how space-time is warped or curved, the speed of light moves at the speed of light, no faster, no slower. And so even though you're shooting it from the Earth, moving through the solar system, rotating, moving through the galaxy, the speed of light shoots out at the speed of light and comes back. And that's why the measurement.
Yes, relatively.
Was that a pun?
This was.
Okay. Yeah, super interesting. Cool applications. And it's been around for a while, but...
Long time.
So this basically is another form of proof for relativity, for Einstein's theorems. So was there any doubt that they were explaining the universe as it was? Or is this just, we were 99% sure, and now we're 99.999% sure. Is that how it was? You know?
Well, when Einstein published all of his documents, his papers, it was within 1 year, 1905. It's referred to as his miracle year. And after those documents were released, there was a huge commotion because they were absolutely incredible. I mean, they changed the way physics worked, because Newtonian physics doesn't apply to things going close to the speed of light because it falls apart.
Right.
Because in Newtonian physics, you can go beyond the speed of light, no problem.
Yeah.
In Einsteinian physics, you can't get, humans cannot even get close. It would be nearly impossible
Right.
because materials would just fall apart. Because of his very famous equation that everybody knows, E equals mc squared, which is the energy mass equivalent. And that says that if you're approaching the speed of light, your mass and energy increases so much that the amount of energy you need to keep going would be unachievable.
So yeah, what happens is like you have this exponential curve, and you can constantly increase to like 0.9c, 0.99c, 0.999c, but you can never reach
Right.
c. So you asymptotically approach c, but your energy required to do so asymptotically approaches infinity.
Yeah.
And as much as we
Gotcha.
like to talk about infinite energy, you can't have infinite energy.
That makes sense.
Exactly.
Moving away from the whole math thing that I don't entirely understand
Yeah.
beyond
I
this.
don't think any of us understand entirely.
I don't think anyone understands. What does the proof of gravitational waves and the ability to detect them mean for the future of space exploration research, astronomy research, and what discoveries do you think could be made, or observations that we couldn't do before we knew that this was possible?
Well, I do know that once the discovery was announced, a whole new type of physics opened up called gravitational wave astronomy. And that is a whole new field indulging into something that I have no experience with. It's very, very complicated stuff.
So that's basically, rather than using telescopes and any type of telescope where you're observing light,
Right.
and for astronomy, but gravitational wave astronomy would be observing gravitational waves and
Right.
not light. It's just
Yeah.
a different way of looking at things that are there.
It could reveal more about the Big Bang, because the way we have learned so much about it is through the cosmic background radiation and reading it in some way. And I believe in my reading, it says that if we could observe gravitational waves from the Big Bang, we would be able to see new things that we weren't able to see before. So that could be a whole new explosion of information. I mean, that has unlimited ideas coming out of
Yeah.
it.
There's a lot of potential in this new gravitational wave astronomy because you have a lot of challenges in regular astronomy looking into the past, where the farther away things are, the more back in time they are. You have something called the inverse square law, where that energy from whatever event in the past gets spread out over such a massive distance that it starts to blend into that cosmic background radiation. It gets blocked by cosmic dust.
Right.
It gets overshadowed by near stars. So if we want to be able to see things that are at the edge of the universe, the edge of the observable universe, we need a new way of detection. And with gravitational waves, because they're such strong events, right? We have two black holes colliding into each other,
Right.
creating these massive waves. We can, when we read them, they're very, very faint, but they're not disturbed like a lot of the light we get.
Right. So, like, the way we look into the past is because a certain photon would be created long ago and has traveled all the way to us and
Right.
took that much time to get to us, and that's how we can observe the past. Would it be able to help us detect dark matter too?
It might. That's a very big possibility. Dark matter is a very ambiguous idea. It's a very difficult idea as well. It hasn't been directly observed. It's been theorized. People have used it in experiments.
Isn't dark matter just dust and remnants of like particles?
It's hard to say because dark matter supposedly makes up about 70% of the universe.
Right.
Because we can see about about 38, approximately 30% of the universe. And that does not account for all the matter in the universe. And that's what we think dark matter is, the matter that we can't see.
So we observe all the effects of matter that should be there, but
Right.
we can't. When we look that direction, we don't see anything.
Exactly.
It's dark. Right?
So it's not dark in the sense that doesn't produce or reflect light that we can observe.
Mm-hmm.
It's just matter, it's mass and matter that we can detect its interactions, but we can't detect its presence.
We can't
easily.
observe it.
Right? It's
Right.
not something you can shine light on and get information back.
So how could a gravitational wave help us detect that? Is that something
So
that's only being theorized?
the main principle, right, is that it has mass and it interacts with other things via gravity. So a gravitational wave, when it interacts with all things that have mass, it would then give us some information about the dark matter.
So when a gravitational wave goes through space and there's a star in the way, for example, does the gravitational field of the star distort the gravitational wave?
It depends on the magnitude of the wave. If it's a very large magnitude, it could distort it, but it might not distort it enough to be measured. But if it's coming from billions of light years away, then yes, I believe it could get distorted by another gravitational field.
My question is, can we look at the nature of the wave that we're observing and extract data from the nature of the wave, not just correlating it with things that we think are happening?
Well, I mean, that's not something that we know, right? I mean, none of us are experts in this field. None of us are even, PhDs in this field. So that's something that's going to take a lot of testing, a lot of, now that they know that one signal is from a gravitational wave, then they can go out and look at different signals and then compare those signals and see what's different about them, what might have caused each of them, and then that's when we can actually get useful data out of it. But we've just seen our first one.
Yeah.
Now I can see, after talking about it with you guys, I can see why people are so excited.
Yeah.
'Cause,
Absolutely. It's a huge discovery.
Yeah.
I've heard people calling it the discovery of the century. It's only 2616, but I mean
So far.
so far Einstein predicted this over 100 years ago with technology that we wouldn't be able to see them with at all. So he had to theorize them. He had to use equations. He couldn't see them. He couldn't measure them. He couldn't do anything with them except theorize them in equations. And the fact that he was able to do that is just unbelievable. I mean, it just adds to his genius, even though he's already...
The thing about Einstein, this is a personal aside. The thing about Einstein is that he looked at the way the universe is and described it with mathematics.
Right.
And haven't read the entirety of his papers, but I'm not entirely sure that there was no chapter, gravitational waves, this is what they're going to look like. It was more like he described the universe as best he could with equations.
Right.
And gravitational waves are something that would happen if you took his equations and you said, okay, what if I have two black holes that come together? That's what would happen, and it was kind of like a byproduct out of it.
Yep.
So the fact that this weird byproduct that is mind-boggling just supports these elegant equations that he just used to describe what he could observe, and I personally, it's kind of inspirational because
It is.
Einstein was a smart guy, but he was also really creative in thinking in ways that other people might not.
It's really interesting. I mean, Einstein is kind of held up as the prototypical genius type, right? But there's so many different people that are geniuses in their one realm. And there's people who aren't even geniuses in their realm, but have such a strong impact, right? Look at Henry Ford. The course of American history, the course of world history, was changed by the things he did, right? If you look at other prominent figures like Andrew Carnegie, right? His approach and his ideas had a huge effect on the way everyone lived.
Right.
like he's not a physical genius, right? But he came up with these ideas and implemented those ideas, and that's really impressive.
That's kind of my point. Like everybody holds Einstein up on such a high pedestal. I mean,
Right.
he deserves it in my opinion, but he's not any different really. I mean, Henry Ford and people like that are just thinking of things differently. And if anybody thinks of things differently, they can have potentially a huge impact on the course of humanity or our understanding of the universe.
So I would say there's a pretty distinct difference between Henry Ford and Albert Einstein.
Of course.
Just in the way that their minds work. Henry Ford was able to make a concept in his mind and bring it to life, whereas Einstein had an incredibly difficult concept in his mind. And he couldn't make it into something physical. He had to make it into mathematical equations, which in its own way is genius. Making something that just moves around in space and being able to formulate a equation that would perfectly describe how it moves. It's just incredible.
I think the key similarity is that both individuals were able to perceive something big, right? Wherein you've got billions of people on this planet thinking millions of ideas. You have just a few people that managed to come up with these ideas, these what we call out of the box ideas.
Mm-hmm.
Now, is that because they're super, super smart? I'm not saying Albert Einstein's not an incredibly smart individual, but
It's not.
I don't think it's
because
just
he's super smart.
I don't think it's because of their inherent
agree.
intelligence. There's something about these people that gives them the ability to come up with a different understanding of the universe. Or in Henry Ford's case, come up with a different understanding of how to build things. That's very impressive.
Right.
I'm just going to go back to this thought one time, drive my point home. It's not that there's anything different about people like that. It's all in us, one way or another, in my opinion. And if you just tap into it, you can have a great effect as well.
True.
I believe in you, TJ.
True.
I believe in you.
Thank you, Phil. But it's just interesting because if we had there's books that talk about this, right? If we have a world of Albert Einsteins, is that the ideal world? Or is it, we had a world of Elon Musk's or a world of Nikola Tesla's? Is that better than the world we have now? Or we have
Hey guys, just jumping in here. This is Phil. Just wanted to say that the rest of this conversation kind of went off on a tangent. We ended up talking about Aldous Huxley's novel Brave New World and how culture and science interact. It really gets pretty interesting, but it's way off topic. So look out for episode 2B, Brave New World. That will be released shortly after this one. So here's a clip from the end of that conversation, and thanks for listening.
I want to mention just one thing that my father told me over intersession break, which really stuck with me. Everything we know is... Well, let me rephrase that. He said, we don't know things. What we know is what isn't possible. We can prove what can't happen, but we can't exactly prove what is. It was a very complicated thought.
And as a sidebar to that, we only know what we can experiment, really.
We only know what we observe.
What we observe.
With gravitational waves, we have another thing to observe. It was a really cool discussion actually on gravitational waves.
Yeah.
And
our Lord and Savior Henry Ford.
So look out for our discussion on Brave New World. Thanks for listening. We'll be back in a week or two with another discussion on space exploration, science, and technology. If you'd like to share your thoughts on gravitational waves, maybe correct some of our mistakes if we made any, or if you have any requests for other discussion topics, please send an email to SPEXcast@gmail.com. This podcast is made possible by RIT Specs, a space exploration student faculty research organization at the Rochester Institute of Technology. Music credit, Kevin Hartnell.